So now we're going to look at what's called the limit of a function. So for example 1, we have the following function, f of x equals x divided by the root of x plus 1 minus 1. And I want to know what is f at 0. So for part A, I can sub 0 in for x, and I get 0 over the square root of 1 minus 1, which gives me 0 over 0. And this tells us that our function is undefined at x equals 0. And if you take a look at the graph to the right, you see at x equals 0, there's a hole in this graph. This function looks like a root function with a hole at 0 and 2. Part B. What is the value of f of x as x approaches the value of 0? So keyword here, instead of saying equals, what is the height of the graph as you approach 0? And there's two ways you can approach 0. You can approach 0 from the right, x equals 0, and you can approach x equals 0 from the left. And you notice as you approach from either side of x equals 0, the height of the graph is approaching a value of 2. So this is what we call a limit. So the function is undefined at 0, but the limit, or f of x, approaches a height of 2 as x approaches 0 from both sides of x equals 0. This would be called approaching from the right side of x equals 0, and this would be the left side of x equals 0. So the definition of a limit. If f of x becomes close to a unique number L, so the height of the graph, as you approach x from either side, then the limit of f of x as x approaches a is L, and it's written in the following format. So the limit as x approaches a for the function f of x equals L, as long as you approach the same value of f of x from both sides of the x value a. We're going to use a graph for this first example, and we can see from the graph that the limit as you approach 0 from the left. So again, this is from the left, so we say this is x approaching 0 from the left. So that's going to be our notation. So we have the limit as x approaches 0 from the left for this function. So what is the height approaching? We can see as you come in from the left, we're approaching a height of 2. As we approach x equals 0, we can see the height of the function is approaching that y value of 2. And keyword, it's approaching. We also see the limit as x approaches 0 from the right for this function. So coming in this direction, 0 from the right, so x approaches 0 from the right. We said it also approaches a height of 2. And since the left-hand limit and the right-hand limit, both of them are the same, then the limit as x approaches 0 is equal to 2. And again, this is the topic of limits. What is the height of the graph approaching as you approach the x value from the left and from the right? So let's look at the following example. What is the limit as x approaches 1 for this function given here? A cubic over a linear function. So one way to look at this, since we don't have a graph, is to test values really close to 1 on both sides. So we're going to check what happens as x approaches 1 from the left and what happens as x approaches 1 from the right. So we're going to get some x values and we're going to check out what does the height of the graph do. If we're approaching x from the left, a number close to that would be 0.9. And then let's try 0.99 and 0.999. So if we sub these numbers into our calculator, you should get the following results. 1.81, 1.9801, and 1.998001. So notice the limit as x approaches 1 from the left for this function is approaching a height of 2. Now let's check the right side. So right of 1 would be 1.1, 1.01, 1.001. So we're getting closer and closer to 1. If you sub these values into the function, you get 2.21, 2.0201, and 2.002001. So again, the limit as x approaches 1 from the right of this function is approaching a value of 2. So we can see that both the left and right hand limits approach a value of 2. So therefore this limit exists and also equals 2. So what does this graph look like? This graph actually looks like a parabola with a vertex of 0 and 1, and then it has a hole at 1 and 2. So as you approach 1 from the left and 1 from the right, the height of the graph approaches 2, but again, this function, if you actually evaluate this function f at 0, we would get 0 over 0. So the function is undefined at 0, however the limit exists. Alright, let's look at the next one. The limit as x approaches 1 of 3x minus 2. So let's check x approaching 1 from the left, x approaching 1 from the right. So we're going to take some x values and sub them into the function. Again, take some x values, sub them into the function. So since we're approaching 1 from the left, we're going to use 0.9, 0.99, 0.999, and from the right, 1.1, 1.01, and 1.001. So again, if we sub these values into the calculator, you get the following results. You get 0.7, 0.97, and 0.997. From the right, we get 1.3, 1.03, and 1.003. So the limit as x approaches 1 from the left for this function, the y values approach 1, and the limit as x approaches 1 from the right for this function, we again see that the y values approach 1. So since these limits are equal, we now know the limit as x approaches 1 is equal to 1. So again, I'm going to show you what this graph looks like. So remember, this is the equation of a line with a y-intercept of negative 2 and then a slope of 3 over 1. There are no holes or breaks in this graph, and we were looking for what happens when we approach 1, so that's this point here, as we come in from the right and from the left. And we see it approaches a height of 1. Now notice this function is what we call a continuous function. There's no breaks or holes in this graph. And let's look at the value of the function itself. So notice if I evaluated f at 1, I would get 3 times 1 minus 2, which equals 1. For many limits, you can actually sub in the x value, and if you get a number, you actually have evaluated the limit, because the function is continuous in many cases at that point. So if possible, if you can sub this number into the function and it spits out a number, that will give you the limit in several cases. Not in all, but for functions that are continuous, like this one, over the whole range, then yes, it's going to give you the value of the limit. So notice here, this is equal to f at 1. Alright, so let's go to example C. Same idea, we want the limit as x approaches 0 this time. So 0 from the left, x approaches 0 from the right. So let's take number 0 from the left will be negative 0.1, negative 0.01, and negative 0.001. And then 0 from the right would be 0.1, 0.01, and decimal 001. You get 100, 10,000, and then 1 million. And we get the same numbers as we approach 0 from the right. So what are these limits equal to then? We see that as x approaches 0 from the left for this function, the numbers get bigger and bigger without bound, so we say it approaches infinity. And as you approach 0 from the right, we get that the height of the function approaches infinity. So we see that in this case, the height of the function does not approach any specific number, So we can say that the limit as x approaches 0 for this function does not exist. Or in some books they say the limit as x approaches 0, since they're both positive infinity, it approaches infinity. So let's take a look at what this graph looks like. So this graph looks something like this. This is a discontinuous function at x equals 0. There's a break in the graph, but notice as you approach from the left, we go up to infinity. As we approach x equals 0 from the right, the height of the function approaches infinity. Next one, this is called a piecewise function. And I want the limit as x approaches 1 for the function given here. Notice the key point here is x equals 1. So let's draw our graph. So first off, it says that when x is less than 1, then it's equivalent to the function x minus 1. So let's draw x minus 1. So minus 1 means we start at the y-intercept of negative 1, and it has a slope of 1. So we go over 1, up 1. But we can't equal 1, so we leave an open dot there. And there is the equation of this line. So x minus 1 exists only if x is less than 1. Let's look at the next one. It says if x is equal to 1, then y is equal to 1. So let's draw that. That's this point right here. So I'll say that's green, that's red. And then the last part, it says when x is greater than 1, then the function looks like a square root function. Notice this square root function has its starting point at 1 and 2, so it happens to start right here. But notice it says x greater than 1, so we can't put 1 in the equation. So here would be your square root function, and that would be the third piece of this piecewise function. So the graph looks like this. So let's talk about the limit now. We want to know the limit as x approaches 1, so we need to check the left-hand limit. What does that equal? We're going to check the right-hand limit. And we're going to use the graph for this one. So as you approach 1 from the left, so that means we are going this way. So we're getting closer and closer to 1. And what is the height of the graph approaching as we come from the left? It is approaching a value of 0. As we approach 1 from the right, so I'm coming in from the right. As I get closer and closer to 1, we see we're approaching a value of 2. So here's a scenario where the left hand and the right hand limits do not match up. And this means the limit at x equals 1 does not exist. They have to be the same, the left and the right, in order for the limit to exist. So since the limit as x approaches 1 from the left for this function does not equal the limit as x approaches 1 from the right for this function, then the limit as x approaches 1 does not exist. However, this function does have a value at 1. What is f at 1? Well, if you look at the graph, f at 1 is right here. And f at 1 is equal to 1. So this function exists for all x. However, the limit does not exist at x equals 1. All right, last example. Using the graph, determine each of the following. So take a moment now, try this yourself, and then check your work. So the limit as x approaches 2. So that means I got to check what is x approaching from the left and from the right. So I go to 2, and I see from both directions it's approaching a height of 1. That one's done. All right, let's go to the next one. 1 from the left. So where is 1? So from the left, we see it's approaching 0. From the right, we see it's approaching 1. Which means that the limit as x approaches 1 does not exist because the left hand and right hand limits do not match up. What about x equals 3? Let's take a look. You see they both are approaching a value of 2 from the left and from the right. And finally, what is the value of the function at 2? So if we go to 2, the only point I see is that f at 2 must be equal to 2. So last part. So conditions under which limits do not exist. The limit f of x as x approaches a does not exist when any of the following conditions are true. First thing, f of x approaches a different number from the left side than from the right side. So that would be like the example we have here. As you approach 1, we have different numbers. The second thing, f of x increases or decreases without bound as x approaches a. So that would be like the example we had up here. The limit goes to infinity. Infinity is not a number, so therefore the limit does not exist. So those are the two cases that you should note. I'd recommend you try the following questions. And I'd like you to think about this question. Rewrite the absolute value function as a piecewise function. If someone wanted you to graph the absolute value of x, how could you write it as a piecewise function? And here's a hint. You can easily rewrite the absolute value function as a piecewise function with two components. So maybe draw it out first and then decide how you're going to rewrite it as a piecewise function. Good luck.